Most developer roadmaps teach you to write code that works on a laptop, but the real job requires writing code that survives GPU memory limits and inference latency. Following a linear path of learning syntax, then building projects, is now a career risk because it ignores the physical constraints of AI hardware that dictate what is actually deployable in production. Today, we connect this headline to the engineering trade-offs behind the hype. We often see colorful, step-by-step guides promising that if you master Python, learn machine learning theory, and then pick up frameworks like PyTorch or TensorFlow, you will be a competent AI engineer. These roadmaps suggest a linear progression where each skill unlocks the next in a predictable sequence. But this model is fundamentally broken for modern artificial intelligence. The reality of 2026 and beyond demands a nonlinear approach that prioritizes hardware awareness alongside software logic. The core failure lies in treating AI as an infallible authority on our own capabilities or career paths. Recent behavioral research indicates that when developers rely too heavily on these generic guides without questioning the underlying physical realities, they make decisions regarding resource allocation and risk management that are 3.4 times worse than those made by engineers who understand the stack deeply. This bias leads to significant financial loss, with earnings dropping between 10% and 42% for teams that ignore hard constraints in favor of AI-approved, but suboptimal paths. Consider the specific mechanics of how software failures differ from hardware failures. A standard study known as Phoenix Bench demonstrates a stark divergence in performance when agents trained purely on software engineering benchmarks are applied to hardware design tasks. These agents see success rates drop catastrophically by 37% to 58% because they cannot bridge the gap between sequential logic and parallel signal flows. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Software bugs typically follow sequential call graphs, where one function calls another in a straight line of execution. Hardware bugs propagate through parallel signal flows across thousands of cores simultaneously. Developers who ignore this distinction will miss root causes in multi-file instantiation chains, leading to production failures that standard roadmaps do not teach how to debug. When you write code without understanding the silicon it runs on, you are essentially guessing whether your model fits into the available memory, or if your latency requirements can be met by the specific bandwidth of the chip. This gap forces a redefinition of what an AI engineer actually does in 2026. The role is no longer just about building applications or knowing which libraries to import. It has evolved into that of a hardware-aware architect who maps software logic directly onto physical reality. Industry practitioners and academic frameworks like Foundations of Gen AI argue that modern success requires nonlinear hardware awareness rather than just knowing the stack. To succeed, you must master three concurrent pillars: inference systems involving kernels and quantization techniques, agent harnesses for RAG loops, and a deep understanding of hardware architecture including RTL constraints. The goal shifts from simply building an app to designing systems where your software logic respects the physics of the silicon it runs on. You need to understand how memory bandwidth impacts data throughput, or why reducing precision through quantization might save you inference time at the cost of some accuracy. The consequences of ignoring this shift are measurable and severe. When developers treat AI advice as absolute truth, they forgo better engineering choices in favor of paths that look good on a checklist but fail under load. This is not just about theoretical knowledge, it is about practical survival. If you cannot explain how your model fits into VRAM or why quantization matters for latency, you are not ready for production. You are simply following a generic checklist that no longer exists in the real world of enterprise deployment. The modern practitioner must constantly ask hard questions during development. Does this specific architecture fit within the memory limits? Is my current strategy costing me accuracy when I could be saving inference time? This shift from syntax mastery to hardware awareness is the only way to build systems that are actually viable for high-stakes environments. It requires you to stop treating AI as a magical black box and start understanding it as a physical resource with strict limitations on speed, capacity, and cost. The evidence suggests that relying solely on linear educational paths leaves you vulnerable to obsolescence. Frameworks change, but the physics of silicon do not. Understanding GPU and TPU constraints is now the primary differentiator between a junior coder who follows tutorials and a production-ready engineer who can navigate complex trade-offs. The ability to map code to hardware capabilities rather than just following a linear tutorial is the core of engineering judgment in this era. You are likely spending months learning frameworks that will become obsolete or inefficient because you haven't learned the hardware layer first. This investment of time without understanding the underlying constraints leads to systems that look good on paper but crash under real-world traffic. The path forward requires a fundamental change in how we approach education and career development, moving away from linear checklists toward a holistic view where software and hardware are co-designed from day one. The stakes are high enough that ignoring them is not an option for anyone serious about their craft. You must audit your current skills against these hard constraints to ensure you are building systems that can survive in the wild. The future of AI engineering belongs to those who understand both the code and the chip, bridging the gap between abstract logic and physical limitation with precision and insight. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.